Okay, good afternoon, and students, I welcome you. The revision lectures now we are taking, and this time we are giving revision of electrochemistry. Student, electrochemistry,
Yes, sir.
electrochemistry revision class. Now, what we have studied in electrochemistry. What is electrochemistry, student? You already know that when electric current is passed through certain electrolytes, electrolysis can take place, or when chemical reaction take place, then we can get electricity. So conversion of chemical into electrical or electrical into chemical, all this forms the part of the electrochemistry, students. The first thing which we studied in electrochemistry was, student, galvanic cells. What is a galvanic cell? A cell which can convert chemical energy into electrical energy.
Yes, sir.
And you have seen the first cell which we have discussed and was made was Daniel cell. Daniel cell, student. What we have to understand, what are the reactions which are taking place in the Daniel cell, student, under standard conditions. So when
Mhm.
this cell is was made under standard condition, you know what are the two half cells. Every cell has got two half cells, you know, students. At one half cell, oxidation takes place. At the other, reduction takes place. Are you familiar with this? So what was the reactions which were taking place in the Daniel cell, students, where the oxidation takes place? Zinc and zinc sulfate solution and copper sulfate solution, the two are joined together by a salt bridge, student.
Yes, sir.
Okay. So what are the reactions, electrochemical, what are the reactions at anode and cathode, student? At anode, oxidation takes place, at cathode, reduction takes place, student. What are the reactions? So how do you write them? Per student, and then what you do, net reaction, cancel the electrons, net cell reaction, student.
Mhm.
What is the net cell reaction in the case of the Daniel cell, student? And under standard condition, what was the value which was obtained for the Daniel cell, you know?
Sir, 213 kilojoule per mole.
Huh?
213.
What was the value of the, was the value of the standard cell potential in the case
Sir,
of
230.
cell? It's also a galvanic or voltaic cell.
Yes, sir.
What is the value?
Sir, 213 kilojoule per mole.
Array, I'm talking of E value in volts for Daniel cell.
Sir, 1.1 volt.
1.1 volt is the value which we get in the case of the Daniel cell. So the for Daniel cell, what you got, E cell 1.1 volt, student. So 1.1 volt is there if, and in the book you will see what they have shown you, that if external voltage is more than 1.1 volt, then the reverse reaction will take place. Reverse reaction can take place if the external voltage is greater than 1.1 volt.
Yes, sir.
If the external voltage is greater than 1.1 volt, student, then what will happen? Then no flow of current, electrons or current, no chemical reaction. The reverse will happen, and the result will be what? Student, that it will electrolytic cell. It will behave like electrolytic cell. Then it will behave like electrolytic cell, students. The reverse will happen. The reverse will start happening, student. Here we have done some mistake in this case, student. Some mistake. The zinc is undergoing oxidation. We
Hmm.
written wrong. Zinc is undergoing oxidation, student. This is 2 plus. And
Okay, sir.
copper is undergoing reduction, copper solid, student. So you make it. We must know what we are doing, students. Okay. So student, the reverse will happen means the zinc from solution will start getting deposited at the zinc and copper will start forming copper ions. Further, what we told you, student, any galvanic cell can be prepared by cup joining two half cells. ठीक है? Whenever you join two half cells, what you will get? A cell. The question is, student, will the cell work or not? That is the point. And
Yes, sir.
what is the, how do we know whether the cell will work or not, student? The value of the cell potential should be what? If this is our standard cell potential. If this is positive, student, then the cell is feasible. So what we will calculate the value of the standard cell potential. How do we represent a cell, students? You have to see how to represent a galvanic cell. What was the how to represent a galvanic cell, students? We said anode on the left side, there is a salt bridge, and we write cathode on the right side, students. So in the Daniel cell, if I have to represent it, student, zinc is undergoing oxidation and copper 2 plus undergoing reduction, student. So we have to mention the concentrations of these ions which we have shown here. What are the concentration of zinc ion? What are the concentration of copper ions? We have to write here. So at anode oxidation, at cathode reduction, this is a way to represent a cell. And how we calculate the standard cell potential value, students? What is the E cell? E right minus E left,
Left, yes, sir, left.
or E cathode minus E anode.
Node.
So we know how to calculate these values. And because students, can we determine the absolute value of the half cell? When we represent these values like this, these are called the standard reduction or electrode potential value, student. And we told you these are under standard conditions.
Yes, sir.
298 Kelvin and 180 M pressure. You will see that they are mentioned. And 1 molar concentrations. 1 molar concentrations
Yes, sir.
in which the electrodes are immersed, student. Okay, since it is not possible, students, to determine the absolute value of half cell. It is not possible to determine the absolute value of the half cell, students.
Yes, sir.
Therefore, what was done? Standard hydrogen electrode.
Okay.
So every cell is joined with standard hydrogen electrode, and then we measure the potentials. That is what we call a standard electrode potential value. Students, standard reduction potential values were obtained by joining each half cell with standard hydrogen electrode. So what is the standard hydrogen electrode, student? We
It's a
already have
standard.
told you in the lectures how to make the standard hydrogen electrode. So you have a platinum electrode, and in that you pass hydrogen gas at 1 atmosphere and 1 molar concentration of H ion. Student,
Yes, sir.
what is the reaction which is taking place? This reaction is reversible. This reaction is reversible, student.
Reversible.
How do you represent it? You have a platinum is an inert electrode, student.
Yes, sir.
So hydrogen gas H plus aqua, student. So this is your hydrogen half cell. And what is the value which was assigned to it arbitrarily? Arbitrarily, student, this is assigned a value
Yes,
of
sir.
how much? What is the value
Um,
of the hydrogen?
2 minutes, sir.
E naught 0.
Sir, 0.02 volt.
0 volt is the value which is given to the standard hydrogen electrode. This value has
Yes, sir.
been assigned arbitrarily, students. Standard hydrogen electrode value is 0 for the hydrogen.
Yes,
So
sir.
students, if we make standard hydrogen electrode as anode and couple it with other electrodes, other half cells,
Hmm.
then what we will get, student? The value of the cell potential, because the value of hydrogen is taken as 0, that will be the standard electrode potential or reduction potential value of the half cell. So what we
Yes,
will
sir.
get? Standard reduction potential, or this is also called standard electrode potential value. Standard electrode potential values of the different half electrodes. So we can obtain these value by joining with this, student. And for example, if we are joining with the copper, then we can measure the EMF of the cell. So
Yes, sir.
if I have, if I join platinum solid, this is my hydrogen. Hydrogen is the anode, student. Hydrogen is the anode. The pressure is 1 bar pressure. Standard conditions means 1 bar pressure. Standard condition means 1 molar concentrations of the electrolytes, 290
Yes, sir.
Kelvin, 180. So 180 pressure, 1 molar, 1 molar. This is our standard electrode which is acting as an anode. And if I have copper 2 plus aqua, student, I should take 1 molar for standard conditions, then it is being reduced to copper. So in this case, if I say what is the value of the cell potential, what is the value of the standard cell potential of this, student, that is E cathode minus E anode, or E right, E naught right, E naught right
Sir.
minus E naught left, student. If I represent by this standard value representation. So here the what is the right side, student? That cathode is this one and anode is hydrogen. This hydrogen is always 0. So basically what we will get, student, the value minus 0. So you will be able to get the value of the E naught. If you measure it by the voltmeter, in this case, if you use standard condition, what we get, student, a value of 0.34 volt. This comes to be 0.34 volt, student. So that becomes the value for the standard electrode potential of the half cell. Because hydrogen is zero, we are taking hydrogen as zero. So by this way, we have been able to obtain the standard values of the half cells
Yes,
of
sir.
whatever elements you want to determine. And then we have constructed a table, student, which you have seen. That is called electrochemical series. There is a table, there are standard hydrogen electrode values are given, student, in a series which is called electrochemical series, for which a table has been provided in the book, where the elements have been arranged according to descending or ascending order of their standard electrode potential values.
Yes, sir.
For example, what you have F2 plus 2E, this gives student value of 2.87 volt for the fluorine. These are showing that these elements are having strong tendency to get reduced. Therefore, they are very powerful oxidizing. This is the strongest oxidizing agent. You are aware of these, students. And in the table, you will see different values. You have AU3, AU3 plus 3E. These values are given in the book table, student. So we have to see from the book what are the values,
Yes, sir.
not to be remembered, but they will provide you the values of this. These values will be given to us in the exam when they will give questions to us, student.
Okay, okay, sir.
Ag plus E, for example, Ag. These are the standard reduction potential. They are also called the standard electrode potential values. What they are called, students?
Yes, sir.
Standard electrode potential value. So it may be around 0.80, like that. Hydrogen, what is the value of the hydrogen? Zero. We have taken it as a 0 volt for hydrogen.
Mm.
Similarly, we have for other students on the bottom will come mostly if you have Zn2 plus 2E, student, this value we
Mm.
know because we have used questions. We have solved questions, students. Based on this,
Yes, sir.
calcium 2 plus 2E, they are metals. Metals will have like negative values of reduction potential because they have strong tendency to lose the electron. Calcium is minus 2.87, and you have potassium. So these values are available in the table which is given in the book, student.
Yes, sir.
If we need, we can see them, but in the question papers they will give us the values of these. These are also solid. So here we are giving you some of the values of the reduction potential. Values reduction potential minus
Yes, sir.
3.05. So fluorine is the strongest oxidizing agent, as you can see, and lithium is the strongest reducing agent. These values are called the electrode potential values or
Yes,
standard
sir.
reduction potential at 298 Kelvin. Standard electrode potential values are also called standard reduction potential values. Okay, we can do all this. Then the next part, which is important, student, where questions are coming, Nernst equation.
Yes, sir.
What is the Nernst equation, students? That if we want to determine the value of the electrode potential of half cell or
Hmm.
any cell at any given concentration, at any given concentration, then how will we
Yes,
do
sir.
it? Because the standard values are calculated at 1 molar concentrations and 298 Kelvin and 1 atm. If I change the condition, student, then how will we calculate the value of the electrode potential at any concentration? We want to calculate the electrode potential at any concentration. We are still assuming temperature and pressure to be constant.
Yes, sir.
So students, we have told you for Mn plus N gives M. This is my solid, student. This is my aqueous. Then Mn plus at any concentration was proposed given by Nernst equation, which he says is the standard electrode potential value, and minus RT of NF of log of ln of natural log
Yes, sir.
of this divided by Mn plus. This value is taken as 1, is constant, and it comes out to be E naught Mn plus by N
Yes, sir.
minus R is gas constant, T is the temperature 298 Kelvin, T is 298 Kelvin. These values are fixed, student, and R is our gas constant. Gas constant here it is taken in joule because energy is involved, 8.314 joule per Kelvin per mole, student. R is constant, T is constant, F is Faraday, which is equal to 96487 coulomb. If we put the values of this, student, then this becomes simplified 0.059 ln.
Hmm.
We convert into 2.303 log. So
Yes, sir.
0.05 by n, student. This is 1. So what it will be? Molar concentration of this ion. If I know this, then I can find the value of this.
Yes, sir.
For a general reaction, A plus B gives C plus D, student. If there is a general reaction, then you know what is the general formula for this, student. General formula is given as E cell is equal to E naught cell, student, minus 0.059 by n, and I can write ln of q, student. Q is the quotient. What is q? Reaction quotient we have studied in the chapter of equilibrium. Q is C power C, D power D, A power A, and B power B. So
Yeah,
I
yes, sir.
can replace those values here and get a relationship between E cell at any concentration and E naught cell is the 1 molar concentration, the standard value of the cell potential, which you already know that E cell will be equal to E naught right minus E naught left.
Left, yes, sir.
These values we will be using it for the solution of certain numericals, which will be important in the exam, student. Then important relationship between equilibrium constant, student, and the value of the E naught cell. This relationship can be obtained, student, by using the Nernst equation. What the Nernst equation is, student, for any general reaction we know. For example, for Daniel cell, have a Daniell cell.
Yes,
How
sir.
do we represent Daniell cell, student? Z and S, copper 2 plus aqueous. What it gives, students? Zn2 plus aqueous and copper salt. This is the Daniell
Yes, sir.
cell. And what is the Nernst equation? E cell will be equal to E naught cell standard electrode potential value minus 0.059 by n, student, log of concentration of Zn divided by concentration of copper ions. What
Yes,
will
sir.
happen at equilibrium? At equilibrium, student, E cell will become zero, equilibrium. Then what is the formula? And this value will become Kc. So what you get? E naught cell, student, is equal to 0.059 n log of K,
Yes, sir.
or Ne cell divided by 0.59 is equal to log of K, students. So this is the relationship between equilibrium constant and the value of the cell potential. If we know this value, we can calculate log C, and then I will take the anti-log and I will get the value of the Kc, student. Important for
Yes, sir.
numericals, important relation for numericals. Okay, all right. Another important relationship we have given you, student, electrochemical cell and Gibbs free energy. Electro, all this will be for numericals will be asked. Electrochemical cell, student, and Gibbs energy. What is the relationship, student? You are aware delta G0 will be equal to minus NF minus NF E naught. So this value is important. If the standard cell potential is known, we can calculate the value of the Gibbs for standard Gibbs free energy change for the reaction, students. You
Yes,
can
sir.
see that delta Rg0 is an extensive property. It depends on the moles, student. N is the moles of the electrons used in the reaction. Extensive property.
Yes, sir.
It is an extensive property. So it depends on n value, student, the number of moles of electron involved in the reaction. If they will increase, the value of delta Rg will increase, whereas E naught cell is intensive property, student.
Yes, sir.
It does not depend on the mole or quantity of the substance. So we already know further relationship was given, student, and delta Rg is also standard if I take equal to minus RT ln K, student, where K is the equilibrium constant. These values are related. Why we need them? They will be used for solving numericals, student, for the exams. This is the first part of the electrochemistry. Tell me, you are aware of these formulas? These formulas are, you
Yes,
are
sir. Yes,
aware,
sir.
there will be questions and numericals on this. ठीक है?
Yes, sir.
Okay. Second, you are aware of electrolytic solutions and conductance. Conductance in solution, students. And you know the formulas which we told you for solving questions. The resistance is directly proportional to length. ठीक है? The electrical resistance is directly proportional to length and inversely proportional to area of cross section of the conductor. And we said
Yes, sir.
R is equal to rho L by A. Where rho, what is the rho, student? Rho is the resistivity. Rho is the resistivity, student. ठीक है?
Yes, sir.
And what are the SI units of R? Ohms. SI unit of R's are ohm, student.
Yes, sir.
So the inverse of the resistance, is what we call a student conductance. Conductance. Okay?
Mm-hmm.
So the same formula can be used for solutions also, where we are saying G is the conductance. So what will be the units of G? Ohms inverse, or you will write like this. This is also called Siemens. S. Siemens.
Yes,
These
sir.
are the units of the conductance, students.
Mm-hmm.
And 1 by rho, what we call 1 by rho, that is represented as a conductivity, kappa.
Mm-hmm.
We are just telling you the things which we are using, student. So what will be the units of conductivity, students? What will be the units of conductivity? What will be the units of conductivity? 1 by rho. What will be the units of specific resistivity? What are the units of specific resistivity, students?
Mm-hmm.
This rho, units of rho. We can calculate from this formula. What is rho? R into A by L.
Mm-hmm.
What is R? Ohms
Yes, sir.
into SI unit. If I have to write, A will be in meters here and meter. So Simon meter. Then what is the unit of ohms? What is this already? Ohm meter. And 1 by rho is your conductivity. What will be the unit? 1 by rho into meter, student. So what you are getting then? 1 by rho is rho inverse, meter inverse. What is rho inverse? Simon meter inverse. Since meter is larger, we are using most of the time centimeter inverse, students. And 1 Simon centimeter inverse will be equal to 1000 Simon
Mm.
meter inverse. Where is my meter inverse? Okay.
Mm. Yes, sir.
These are some of the formulas which we are revising for solving the question, student, for solving the numerical question, which will be used in the chapter of the conductance, conductivity, students. So we have different, there were some values which were given for the values of conductivity was given for conductor students, for insulators, and the value of kappa, the conductivity sign 1 meter inverse. This is the conductivity, and conductors have very high values, maybe around 10 power 3 to 10 students. Simon meter inverse. Insulators will have very low value, 10 minus 16 Simon meter inverse. Aqua solution may have around point 0 to 0.01 to 3.5 something, 10
Yes,
minus
sir.
values. Semiconductors are having value with 10 minus 7 to 10 minus 2 or 2 values in terms of Simon meter. These values are given in the book, students.
Mm.
And the measurement of conductivity of ionic solution, there is a conductivity cell which we have discussed to calculate student the value of the conductivity.
Yes,
So
sir.
conductivity cell we were using to calculate the values of measurement of the conductivity of ionic solutions. Measurement of conductivity of ionic solutions, student. And we have told you in that, student, R is equal to rho L by A, or we can write rho is 1 by conductivity into L by A, students. So R measurements are done, then this conductivity can be calculated 1 by R into L by A.
Yes, sir.
So R measurements are done by using a Wheatstone bridge, student, and therefore we can calculate the value of this. And since L and A for the cell is constant, this is called cell constant. Cell constant, student.
Yes, sir.
Therefore, we can find the relationship between these values R into kappa is L by A, which is your cell constant. This is equal to the cell constant. These are some of the formulas which can be used, student, in order to solve the numericals.
Yes, sir.
Okay. In the lectures we have told you, we also define molar conductivity, conductance of a 1 mole of a solution, student. So what was the relationship? We defined molar conductivity, students. Because if we measure the conductivity value and the concentration of the solutions are different, then there is, how will we measure it? Because concentration will change in concentration, the conductivity values will change. So depending on the concentration of the solution, you know that conductivity of different electrolytes in the same solvent at a given temperature, there will be difference in charge and size of the ions in which they dissociate, the concentration of ion or ease with which ions move under potential gradient. Therefore, a molar conductivity has been defined as conductivity divided per unit molar concentration. So lambda m was given as kappa by C, students. Kappa is the conductivity, C is the concentration, students. So we have to be careful about the units of this when we will see that what units we are using. If lambda m, student, lambda m is Simon centimeter square mole inverse, then you know what are the unit. If the units of conductivity is Simon centimeter inverse, then this will be 1000 centimeter cube per liter, because that is the unit of the 1 liter. And if molarity is given, C is nothing but the molarity. Molarity is given always in mole per liter. So we can see what will be the units of lambda m also has been asked in the paper, the units of lambda. These units are important, students. What are the units of
Yes,
lambda
sir.
m? Simon centimeter square mole inverse. Important point, important question which has been asked in the paper many times.
Yes, sir.
So for the numericals, we have to prepare, student, because there will be numericals on this. You can watch the YouTube lectures which we have given on electrochemistry so that you understand these values and all the molar conductivities which we have discussed, students. So further important point which was discussed was
Yes, sir.
we have discussed the variation of conductivity and molar conductivity with concentration. Variation of conductivity
Yes, sir.
and molar conductivity with concentration. Important question is coming in the paper here. And molar conductivity with concentration, student. First we discuss conductivity. Can you tell me how does conductivity vary with concentration? Kappa. If I decrease the concentration, what will happen, student? Will the conductivity decrease or increase? Will the conductivity increase or decrease? Important question. Conductivity
Yes, sir. Answer decrease.
always decreases with decrease in concentration. Is the conductivity of 1 centimeter cube of solution, because the number of ions will decrease if the concentration decreases in 1 centimeter cube of the solution, student. Number of ions per unit volume will decrease, student, if I decrease the concentration. But we have seen the molar conductivity, student, is inversely proportional to concentration.
Yes, sir.
What formula we gave you for molar conductivity? Conductive kappa by C, inversely proportional to concentration. But it also, there are two factors. The change in concentration is more pronounced than the change in conductivity, students. Therefore, what will happen? There are two cases. Case 1, weak electrolytes. For weak electrolytes, what happens, student? If you study the variation in molar conductivity with the concentration, what type of graph you are getting?
Yes, sir.
What type of graph you are getting in this case, student? For weak electrolytes, there was a sharp and sudden increase in the molar conductivity on dilution in case of weak electrolytes. There are two cases, student, weak and strong. The graph is important because this will be asked a lot. Lambda m, student. What are the units of this? You already know, Simon, centimeter square, mole inverse, and you plot against square root of C. Square root of C, concentration. Student, that is molarity, mole per liter 1/2, students. Do you know the graph which we are getting for weak electrolyte? Important question, student, here. That was for
Yes, sir.
acetic acid. And for strong electrolyte, what you got? There was a small change like KCl. So these are the graphs which let me make it little that graph.
Yes,
That
sir.
was the KCl. There was a slight increase in the dilution, and for this we have seen this is a weak electrolyte. Acetic acid. For the strong electrolytes, we know that what is happening. The strong electrolytes are completely ionized already. And what happens, student, when you will dilute them, then what will happen? There is only slight increase in the conductivity because the interionic forces of attraction will become weak. That is the reason there is
Yes, sir.
increase in conductivity. For this, we have given a formula lambda m is equal to lambda 0 m minus a root c. So this is a linear relationship which we have shown you. Lambda 0 m is called the limiting molar conductivity. What is this called? Limiting molar conductivity.
Yes, sir.
Conductivity at infinite dilution. This is the limiting molar conductivity. Conductivity is at infinite dilution. This can be obtained from this graph in the case of the strong electrolytes. But lambda 0 m cannot be determined for weak electrolytes, as you can see the graph. This will not be meeting that it will meet only at infinity. Therefore, you can see the difference between the two students, strong electrolyte and weak electrolyte.
Yes, sir.
And there will be questions on this, which you have to answer in the paper. Very important, student. So in weak electrolyte, the degree of dissociation you see at higher concentration is very small. On dilution, more and more ionization takes place, and therefore more ions will be produced on dilution. That is why you see there is a abrupt increase in molar conductivity on dilution in the case of the weak electrolytes. So at infinite dilution, they will be completely ionized. They will be completely ionized, and if you want to determine their values, this will be determined by what we call as the Kohlraush law of independent migration of ion students.
Yes, sir.
What is Kohlraush law? This is important for example. Of independent migration of ions. What is the Kohlraush law of independent migration of ion, student? At infinite dilution, the limiting molar conductivity can be of an electrolyte can be represented as sum of the individual limiting molar conductivities of all the anions and cations of the electrolyte, students. That's what we said. So if you have NaCl, student, what happens? This will dissociate completely in the solution. It's a strong electrolyte, and you said the limiting molar conductivity of NaCl can be written as limiting molar conductivity of sodium ion plus limiting molar conductivity of chloride ions. And if what happens, student, if there is a electrolyte which gives V plus cations, if the electrolyte, student, produces V plus cations and V minus anions, students, ठीक है. Then the
Yes, sir.
limiting molar conductivity of the electrolyte can be written as molar conductivity of the electrolyte can be written as V plus, where lambda plus is the molar conductivity of the cation, plus V minus lambda 0 minus. So molar conductivity of the cations plus anions, and this is the number of cations, and V minus is the number of anions total.
Mm-hmm.
This formula we told you, student, very very important formula for the molar conductivity. An important relationship we have discussed, student. Now lambda alpha is the degree of dissociation. This is related with the molar conductivity divided by the limiting molar conductivity.
Mm-hmm.
So using this formula, student, we can calculate lambda 0 m, the limiting molar conductivity for weak electrolytes.
Yes, sir.
For weak electrolytes, students, by using this formula. And also we can calculate the dissociation constant for weak acids. What is the formula for the dissociation constant of the weak acid, students? Dissociation constant for the weak acid. What is that formula?
Mm-hmm.
Dissociation constant of the weak acids. You already know, students. For a weak acid like acetic acid, we have derived that formula earlier also.
Mm-hmm.
What happens when they dissociate? You have water exposing. So how we define Ka, student? CH3 CO minus H3O plus. Water was in large amount, so we took it constant, student. So if it was in the beginning, C amount of this was present, and if it alpha dissociates at equilibrium, then this is C alpha and C alpha. So what did it become? C alpha into C alpha, C1 minus alpha C. Since alpha is much much smaller than 1, we say 1 minus alpha is almost equal to 1. So what is the relationship then? Ka is equal to, students, or you can write Ka is equal to C alpha square 1 minus alpha. Put the value of alpha from here. What is alpha? Our alpha, we have already said lambda m by lambda 0 m. So you put the values here, what you will get? C, this is lambda m by lambda 0 m, and what is this? 1 minus lambda m by lambda 0 m. So we can derive a relationship. You can simplify this and you will get, students, and this will take the LCM of this.
Mm-hmm.
You will get, student, lambda m, lambda 0 m. So what is the result of this? Now finally you will get some answer. You can lambda m square. This will be our lambda 0 m. You can take the LCM, and lambda 0 m minus lambda. So this way we can calculate the value of Ka also, which is the dissociation constant of the acid, students. These are some of the important points, student, in the chapter of the electrochemistry, and this is the first part of the revision. In the next lecture I will give you some questions on this, what we have discussed. We have questions which will be given in the next class now, because our time is running out, but we have revised the complete chapter. ठीक है? So
Yes, sir.
you come prepared. Tomorrow we will take questions on this. You come prepared with the question answer sessions so that we can discuss the questions, all the units, everything which we have discussed, student, in electrochemistry. Non-stick equation questions will be there,
Mhm.
and numericals, everything can be asked. Objective type, assertive type, all type of questions can be there. ठीक है?
Yes, sir.
Okay, then we will meet you tomorrow. I will tell you the time. So we'll have a class on some problems of electrochemistry tomorrow.
Yes, sir.
Okay, then I will see you in the next class.
Okay, thank you, sir.